Hello, good evening, everyone. I think we can start the session. Today is the week 3 of this class, and basically we'll be discussing about Fourier transforms in general. In the last class, we have discussed about Fourier series. We have solved a couple of problems on distinction between periodic and aperiodic signals. We have found out the time period of the signal. Other things that we have done previously. Here in this class, that is today, we will look into continuous time Fourier transform. We will look into we will also understand some of the properties of the Fourier transform, and also solve a couple of problems on Fourier transforms in general. So that's the objective of this class today. Okay. So I'll share my screen. So I think my screen is visible to everyone, is it? If anyone can kindly confirm. Hello?
Yes, sir.
Okay, fine, fine. Okay, okay. As I have already given a introduction about myself in the previous weeks, so I think it's not required anymore. So, as I already told, today we'll be discussing about Fourier transforms in general. In the preceding weeks, that is week 1 and week 2, we have looked into various things. For example, in week 1, we have talked about biomedical signals in general, particularly about biomedical electric signals like EEG, ECG, etc. We have talked about different types of signals. We have talked about different types of system and how to distinguish between the various types of systems. This were the things that were done in week 1. In week 2, we have done a Fourier series. We have talked about periodic signals in general, and what are the conditions of our Fourier series, and solved a couple of problems on Fourier series and periodic signals. Okay. Today we will be talking about Fourier transform, and more particularly we will talk about continuous time Fourier transform. So what basically is Fourier transform? That's very important to understand for us. It's basically a mathematical function or a tool that takes a time-based pattern as input and determines the overall cycle offset, rotation speed and strength for every possible cycle in the given pattern. So this is the actually the physical interpretation of why are we doing a Fourier transform and what is the necessity of Fourier transform. So I think everyone understood it. Then we will go into the mathematical formulations of Fourier transform, which every one of you are well acquainted with. Okay. First, let us understand the condition for Fourier transform. So we know Fourier transform does not exist for all non-periodic signals. Hence, for a function that is xt to have Fourier transform, the following conditions called Dirichlet conditions should be satisfied. So the first condition is that is the function that we have should be absolutely integrable over the interval minus infinity to plus infinity. So I think everyone remember this condition was a bit different in the Fourier series. Okay. The function x of t should have a finite number of maxima and minima in every finite interval of time. And the function x of t has a finite number of discontinuities in every finite interval of time. Also, each of the discontinuities must be finite. So these are the actually the conditions, that is the three very important conditions for Fourier transform. And we know a function, these are the and we also know that these are very important for a function, so that we can find out the Fourier transform for it. And we all know that Fourier transform has immense uses from in the signal industry since time immemorial. Okay, so this is the mathematical interpretation of Fourier transform. Let us consider we have a time signal, that is a signal in time domain, and let us denote this signal as x of t. Now, the Fourier transform, that is the frequency transformation of the signal, that is x of omega, can be defined as minus infinity to infinity x of t e to the power minus j omega t dt. So this equation, where we have a time domain signal x of t and we find out the frequency transformation of that signal, this is called analysis equation. So this is very important. We should understand and should know what is this equation called. Now, for example, we have the Fourier transform signal with us, that is x of omega. And our objective is to find out the time domain signal or the original signal from the Fourier transform signal. So the signal x of t can now be defined as 1 by 2 pi minus infinity to infinity x of omega e to the power j omega t d omega. And this equation is known as synthesis equation. This is known as synthesis because here we are performing an inverse operation. That is, here we are having a Fourier transform signal and we are actually obtaining, and or else our objective is to obtain the original signal from the Fourier transform signal. So these two equations are very vital and very important, actually very important for the Fourier transform study in general, rather be in solving numerical problem or in solving real-time problems. We all know that Fourier transform has immense uses in the signal industry. For example, I can give a very simple example of Fourier transform. Like for example, let us consider we have a signal x of t, and a signal doesn't necessarily should be a one-dimensional signal. Like there can be two-dimensional signal, and these are called images. Now, for example, I can give you a simple example where Fourier transform is used to some extent. Obviously, some advanced type of transformations are now rapidly used in industry. For example, wavelet transformation, empirical wavelet transformation, and various advanced transformations. For example, you have an image, okay, and your objective, for example, you have not you don't have a single image, but you have a number of images. For example, your objective is to classify an image and tell me whether this image has cancer or not. And let me for instance consider that you have a mammogram. I think everyone knows mammogram is nothing but X-ray of the breast. Okay, so let us consider we have mammograms with me, and I know, or the doctor has already given a definition that which of the images are cancerous and which of the images are not. So there are various approach of classifying it. One of the approach may be a machine learning approach, and as we know in a machine learning approach, our objective is actually to find out handcrafted features, which is obviously not required in a deep learning architecture. If we want to build a deep learning classifier, our task will be to pre-process the image and directly feed that pre-processed image into the DL architecture. But for instance, we do a machine learning thing. Then first objective is what? We have an image. Then from that image, we have to obtain handcrafted features, and these handcrafted features can be filtered. We can perform some feature selection, and then the feature that's selected will go to a final classifier. So all of you might think that where is the usage of Fourier transform or transformations like wavelet transformation? The advantage or usage of these transformations are in the feature extraction side. That is, you have an image and you have to find out some handcrafted features. So here what you do is you have the image, you go for the 2D Fourier transformation of that image, and the 2D Fourier transformed image you can obtain various features. You can define your own features, and these features can directly go for features selection and finally for classification purpose. I think everyone is clear what I said. If you are not clear, you can ask questions. I am ready to answer this. Okay, this is just for your knowledge that where can we use such transformations in our real life. So as I said, as I gave the example for an image, the similar thing can be done for a signal. You can use such type of um, you can use this Fourier transform for feature extraction. For example, you want to classify some EEG signals and tell me that okay, these are the EEG signal of an epileptic child and these are the EEG signals of a non-epileptic child. So this transformations like wavelet or two-dimensional Fourier, here it's obviously not two-dimensional because it's a signal, we'll use a one-dimensional Fourier, can help you to actually extract various kind of features, and these features may actually help in the classification process to a huge extent. Okay, I think everyone understood. Actually, this is my research problem. Actually, I basically work in the field of medical image analysis, where my objective is basically to do this. Okay, I don't know whether this is outside the scope of the class, but this is just for your knowledge. I think it will help you in the long run. Okay, now let's go for the traditional thing that what we were actually thinking of discussing. For example, let me consider that I have a signal of this form. That is, the signal is x of t, which is equal to e to the power of minus at ut. And I think everyone remember what is ut. Ut is nothing but a unit step function. And we have already studied this function in the previous class. We have understood the MATLAB demonstration of unit step. And we all know unit step function is a function where the value will lie from 0 to infinity. That is, the value will be 0 from minus infinity to 0, and the value will be constant, that is 1 from 0 to plus infinity. Okay, and we all know the curve of e to the power minus 8. E to the power minus 8 is actually an exponential curve, and obviously this curve will lie from minus infinity to plus infinity. But as we are multiplying an exponential function with a unit step, so the resultant function which will be there will be a exponential function, but the range of this function will not be from minus infinity to infinity, else it will be from 0 to infinity. Okay, this is clear. Now applying that transformation, or applying the formula that we have studied, let us obtain the Fourier transform x of omega. So writing the traditional formula, that is x of omega, which is equals to minus infinity to infinity x of t e to the power of minus j omega t dt. Okay, and what I said, this function, that is e to the power minus at into ut, will lie from 0 to infinity because we have a unit step, and unit step will lie from 0 to infinity. And it's clear, multiplication of one variable to the another will give a resultant function which is of that type. That is, the function will lie from 0 to infinity and it will be an exponential function. So you can see in the second line, I have changed the range from minus infinity to infinity and written from 0 to infinity because this function lies in this range only. And we have written as the function, the value is equal to 0 to infinity e to the power of minus at into e to the power of minus j omega t into dt. Now again just take t common, and what you will get is e to the power of minus a plus j omega into t dt. And all remember the integration formula, integration of e to the power minus mx dx is equals to minus 1 by m e to the power of minus mx. So using this integration formula, we get the next line as minus 1 by a plus j omega into e to the power of minus a plus j omega t, where the value of t will be from infinity to 0. Then we all know e to the power minus infinity is equals to 1 by e to the power infinity, and e to the power infinity is infinity, so 1 by infinity is 0, and minus e to the power of 0, and we know anything to the power 0 is 1, so ultimately we get a value of 1 by a plus j omega. Okay, this is a very simple problem, and I think it's pretty clear like how is the problem solved. So this is another problem that I will like you to solve for your homework. That is, let me consider the function as x of t is equals to e to the power of at into u to the power u of minus t, and I want you to find out the Fourier transform for this signal. I think that everyone has noted it down, and I will like to do it. If you face any problem, we will discuss it in the next class. Okay. Okay, and obviously we'll solve a couple of more problems. Okay. Is it clear? Is anyone having any doubt or something? Then we can continue with the continue further. It's fine, isn't it? Yes, yes, yes. Yes, that's the only change. Nothing else. Okay, that's the only thing. Uh, like I gave a few, matlab, a brief description about the usage of Fourier transform in the image processing and the signal processing side. Like, was it clear? Did you all understand? I think you have even pretty much used those kind of transformation in your image processing or signal processing projects. Is it so? Okay, then fine, fine. Let's continue with the uh, further problems. So this is the question that I will like to do, like you to do in your home, do in your homework. Fine. So let me consider another problem. Okay. So another problem. Obviously, we have a time domain signal x of t, and our objective is actually to obtain the Fourier transform x of omega. And for instance, the signal let the signal look in this manner. Let us consider we have a square wave, or we can say rectangular wave, whatever, and the value of this pulse will be from minus t to t, as it's written. X of t is equals to 1 from the range of minus t to t, and it is 0 elsewhere. So this is the function that we have defined. It's a rectangular pulse, as we call it. Okay, and our objective is actually to obtain uh, the Fourier transform for this pulse. So if you check this problem, so x of omega is what? It is equals to minus infinity to infinity x of t e to the power of minus j omega t dt. Okay, and instead of x of t, what we will write here, it's 1, but I think you can see that the range has changed from minus t to t, because obviously the function lies from minus t to t and it's 0 elsewhere. So what's the use of writing the entire range? So what we do is we reduce the range from minus t to t, and it will be 0 elsewhere, and obviously the value of this function is 1 between this range. 1 into e to the power of minus j omega t dt. So again, applying the same integration formula, this integration of e to the power mx dx is equals to 1 by m e to the power mx. So similarly, integration of e to the power of minus j omega t is equals to minus 1 by j omega e to the power of minus j omega t, and the range will be from minus t to t. So we know that minus 1 by j omega into e to the power of minus j omega t minus e to the power of j omega t. Now shift the negative sign, and then what we will have is e to the power of j omega t minus e to the power of minus j omega t divided by j omega. Now we know, that is, we know what is sine theta. We know that sine theta and cos theta can be expressed in the form as written above, as written here. So sine theta can be written as e to the power of I theta minus e to the power of minus I theta divided by 2i, and cos theta can be written as e to the power of I theta minus e to the power of minus 2 I theta divided by 2. I think everyone knows how to find it, because we know that e to the power of I theta is equals to cos theta plus I sin theta. And this is clear. If anyone has doubt, please kindly tell me. So what we can do, so what we have with us is e to the power of j omega t minus e to the power of minus j omega t divided by j omega. But we can see that sine theta, for obtaining sine theta, for writing in terms of sine, what we have to do is we have to have a denominator of 2. So what we do is we multiply numerator and denominator by 2. So what we have with us is e to the power of j omega t minus e to the power of minus j omega t divided by 2 j omega into 2. So which can be written as equals to 2 sine of omega t divided by omega. And what is this actually? This is actually a sinc function. We all know what is a sinc function. So it is seen that the Fourier transform of a rectangular pulse is actually a sinc function. This is obtaining the Fourier transform of the signal. We have the original signal, time domain signal, as rectangular, and the Fourier transform signal as sinc function. I would like you to solve another problem. If you can please note it down. This will be for your homework. For instance, let us consider that you have a Fourier transform signal. Means here you have to obtain the inverse Fourier transform, not the you have to go for the inverse Fourier transform, not the Fourier transformation. And I am considering the input is again a rectangular pulse, but in Fourier domain. That is, I am telling an input which is equals to x of omega is equals to 1, where omega is lying between minus pi to pi. Okay, you can note it down. The problem, x of omega is equals to 1 for omega lying between minus pi to pi, and the value will be 0 elsewhere. For this problem, you have to obtain the inverse Fourier transform and ultimately obtain the original signal x of t. I would like you to solve this problem. I think everyone has noted it down. If yes, you can try. Yes. There is in the video also, I think you have heard about one problem, that what sir was saying, that the Fourier transform of a rectangular pulse, this one is actually what is the Fourier transform of a rectangular pulse is actually a sinc function. And if you do the opposite thing, that is, if you obtain the Fourier transform of the sinc function, surprisingly you will also see it's a rectangular. I would like you to try for this. I would like you to find out the Fourier transform for the sinc function. And if you have any problem, you can tell me in the next class. Okay. So now let us look into some other Fourier transform for other simple functions. Let me consider the impulse function del of t. We all know what is del of t, or particularly what is impulse function. An impulse function is one where the value will be, or you can say for time domain, the value exists only for t equals to 0, and it will be 0 elsewhere. Means it will be a spike at t is equals to 0, and it will be 0 elsewhere. Okay, so if I find out the Fourier transformation for the impulse function, writing the same formula again, that is x of omega is equals to minus infinity to infinity x of t e to the power of minus j omega t dt. Okay, and now replace x of t by del of t e to the power of minus j omega t dt. And what we know, this is a very important statement to state here, that impulse function exists only for t equal to 0. So this function will exist for only t equals to 0 and will be 0 elsewhere. So what do we write? This is equals to e to the power of minus j omega t at t equal to 0. And if you just put the value t is equals to 0, we will get equals to 1, because we know anything to the power 0 is equals to 1. So what is our conclusion? Conclusion is that Fourier transform of an impulse function is equals to 1. So this is another formulation. We know that Fourier transform of a unit step. You can even try it out. If you Fourier transform unit step is equals to pi of del of omega plus 1 by j omega. I'd like you to try this by your own. Tell me if you have any problem. Like these two problems that I have written for you. That is the Fourier transform of a unit step. And another question that I have is Fourier transform of e to the power of minus a modulus of t. So I think everyone knows what is the meaning of modulus. So kindly note these two problems. Please try it out. Okay, try this out. Try these two problems. Okay. Yes. Which one? Impulse function. This one. This one. Yeah. Tell me which place, like in which place did you not understand? Okay, see. This is you know that what you have to understand one thing. What is the value of sine? We can actually write sine theta and cos theta in the form of e to the power of, matlab in exponentials. So another thing that you have to keep in your mind is e to the power I theta is what? E to the power I theta is actually cos theta plus I sine theta. And what is e to the power of minus I theta? That is equals to cos theta minus I sine theta. Okay. Now just replace. Just what you do, e to the power I theta minus e to the power of minus I theta divided by 2i. You just write e to the power I theta in terms of cos theta and sine theta and see what you get. Just replace e to the power I theta as cos theta plus I sine theta. Then what you will get? Minus cos theta minus of sine theta, means ultimately what you will have. So what you will have is cos theta plus I sine theta minus of cos theta minus I sine theta. So cos theta will get reduced. What you will have is 2i sine theta, 2i sine theta, isn't it? And see, and what you have in the denominator is 2i. So what you will get is equal to sine theta. Is this clear? Hello? Yeah, did you understand how are we writing this in the form of sine theta? So what we did, actually what we want to do, we want to again express this exponential in the term of sine function. So what we got here, you see, e to the power of j omega t. So instead of j omega, you consider theta is equals to omega t here. Okay, just compare these two equations, and what you do is just replace theta is equals to omega t. So what you are having is e to the power, obviously I and j are imaginary numbers, the same, doesn't make any difference you are writing I or j. So e to the power of j omega t minus e to the power of minus j omega t divided by j omega. But we know sine theta is equals to e to the power of I theta minus e to the power of minus I divided by 2i. So we don't have 2 in the denominator. So what you do, if we don't have 2 in the denominator, we multiply 2 in the numerator as well as the denominator. So at that time what you will have 2 into e to the power of j omega t minus of e to the power of minus j omega t divided by 2 j omega. Now if you just leave out omega, that is if you write 2 divided by omega, what you can do, you can replace this entire function using a sine function. Is it clear now? Did you get it? It's clear, isn't it? See, what you do is what I told you, can just try it out. Okay, you can just try it out by your hand. If any problem, then you can. I think it's pretty clear now. If it's not clear, you can tell me. I can explain one more time. It's clear. Okay, fine, fine. Okay. Exactly. See, you just see the sign change. You just see minus 1 by j omega, then what you have? E to the power of minus j omega t minus e to the power of j omega t. Now, now there is sign change, that's why I am writing e to the power j omega t minus e to the power of minus j omega t divided by j omega. So sign is getting minus minus, it's becoming plus, na? Yes, understood. Yeah. That's the reason the sign changes. The sign is changing. Now it's from minus to plus. Okay, it's clear, na? Yeah. Okay. So I think it's clear for how did we find out the Fourier transform for impulse function. So the next, what I would like you to do is you kindly try it out. You kindly try these two things. If it's not clear, today last week actually I forgot to send I think my email ID. I will attach this in the chat itself. Any doubt you have, kindly contact me. I can help you out. This is my sorry. It's Gmail, okay? Yeah, other things remains constant, it's just change. Fine. Just solve this two problem and another problem that I have discussed previously. Okay. Let us consider another problem. Okay. So I think who has checked out the checked out the lecture by professor, then they will understand. I think there were various properties that were actually discussed in that class, and using this property we will solve a simple problem. I think everyone remembers the linearity property. Okay, so for example, we have xt equals to x1t plus some another function. So Fourier transform of x of t is equals to Fourier transform of x1t plus Fourier transform of this function. Okay, and the problem statement can be defined in this manner. We have a function which is equal to x of t, and this is actually the summation of two functions, where one function is x1t and another function is 2 of del 3 minus 2t, and everyone knows that del is nothing but obviously an impulse function. And what the problem says is x1t, the signal that we have, is actually a derivative of the impulse function, that is d dt of del t. And if you check the property the properties of Fourier transform, we remember and we see that that is a Fourier transform of a derivative, that is Fourier transform of a signal x of t, which is the derivative. Fourier transform of a derivative of a signal, it is equals to, that is Fourier transform of d dt of x of t can be written as j of omega into x of omega, where x of omega is the direct Fourier transform of the signal x of t. So if we have this property, will make our life easier, and obviously it will help to solve this problem easily. So x1t is what? It is equals to d dt of del of t. So d dt of del of t can be written as, by using this property, j of omega into Fourier transform of del of t. Fourier transform del of t means Fourier transform of the impulse function. And we have checked just now that Fourier transform of the impulse function is equals to 1. So j of omega into 1. So we got that Fourier transform for x1t is equals to j omega. Now we have another function, that is 2 of del 3 minus 2t. And we know that by time shifting property we can write 2 of del 3 minus 2t as 2 of del 2t minus 3. And also by basic signal system we know that we can write the function del of 2t minus 3 as 2 into 1 by 2 del of t minus 3 by 2. Now what we have basically, and obviously 2 will get reduced, so the function actually reduces to del of t minus 3 by 2. And by time shifting property of Fourier transform, we know that Fourier transform, if we have a signal x of t and the Fourier transform of that signal is x of omega. Now if we shift the signal, that is Fourier transform of x of t minus t naught, that is we shift the signal by some time, it is equals to e to the power of minus j omega t naught into x of omega, where x of omega is nothing but the original Fourier transform of the signal x of t. So what we can write by using this property, that is Fourier transform of a del of t minus 3 by 2 can be written as e to the power of minus j omega t naught, and here t naught is equals to what? It's equals to 3 by 2 into Fourier transform of the original signal, that is Fourier transform of del of t, and we all know that Fourier transform of del of t is what? It's equals to 1. So what is the combined Fourier transform of the signal x of t? It is equals to x of omega, x, that is x of omega, it is equals to j omega plus e to the power of minus j omega into 3 by 2. So this is the thing we have. This is by solving the linearity property we have this solution for this problem. Okay. So in Fourier transform, it's very important that we understand the properties of the Fourier transform. We remember those property, and then we apply this property in a very cautious manner, in a beautiful manner. Actually, it will make our life a lot easier. Let's have another problem. So we have again an impulse function, and the function can be stated in this manner. So this is del of t minus t naught divided by a. A is nothing but a constant. So del of t minus t naught divided by a can be written as modulus of a into Fourier transform of del of t minus t naught. And we all know that Fourier, just now we have studied, that is time shifting property of Fourier transform, and I think who have checked the lectures, they have understood in details about this time shifting property of Fourier transform. So Fourier transform of x of t minus t naught, this is equals to e to the power of minus j omega, e to the power of minus j omega t naught into x of omega. And obviously here t naught is equals to t naught, and Fourier transform of the signal, that is del of t or impulse, is 1. We have understood it. So for this function, the Fourier transform is equals to modulus of a into e to the power of minus j omega into t naught. Okay, so these are some of the problems that actually we have discussed. Okay, so these are some of the problems. I would also I would like you to solve a couple of more examples. I would share you this problem. Just wait. Okay. Okay. Uh, so let me consider that we have a signal g of t, and the signal properties are not given to us, but just we have a signal g of t, and let me consider the Fourier transform for that signal is equals to g of omega. Now I would like you to find the Fourier transform for this 4 signals. I can give you some hint. For example, the first one. So the first one is what? G of t minus t naught. So it looks like something like time shifting. It's shifted by 2. So we can apply the time shifting property and get the answer. For example, g of t minus t naught, the Fourier transform of g minus t naught or x of t minus t naught can be written as e to the power of minus j omega t naught into Fourier transform of that signal. So what we can write for this function g of t minus 2, we have the Fourier transform is equals to e to the power of minus j omega t naught, and t naught is equals to 2 here into x of omega, and obviously x of omega is g of omega here, because g of t is not defined, it just sets the signal, nothing else. Okay, and I would like you to do other problems by your own. Any problem, then you can discuss with me. Okay, so another problem that we have, the last one, that is g of 3t plus 1. I can discuss this, other problems are easy. So what we can write, g of 3t plus 1 can be written as 1 by 3 into g of t plus 1 by 3. So this can be written, and then what we have is t plus 1 by 3. So it's again a time shifted signal. So what we have to do, we have to use the time shifting property of Fourier transform and get the solution. I would like everyone to kindly note these problems so that you can try this and maybe your concepts will improve. Okay, so these are the things that actually I had to discuss on to understand and further study about Fourier transforms in general and solving a couple of problems which maybe will help you in solving the assignment problem. I have checked the assignment problem. The assignment looks actually in a similar line. So what we will be doing in the next class, we will be basically understanding or studying discrete Fourier transform. So this is the study that we are doing today, or the problems that we are doing today is basically on the continuous time Fourier transform. The next study, the next class will be based on discrete Fourier transform most probably, and then we will also look into some MATLAB demonstration for this discrete Fourier transform, because discrete Fourier transform has immense uses, as I discussed initially, in the field of signal processing or in the field of image processing, from and it has varied applications, right from feature extraction to help in denoising applications. So it can be used in a couple of problems. It can help you, it can make your life easier. Obviously now advanced transformations are there, but obviously transformations like, or fundamental transformations like Fourier will always have its importance as it is today actually. Okay, so these are the things that basically I wanted to discuss today. So basically I wanted the class to not only be a monologue. I wanted the class so that we'll have inputs from both the sides. So these are actually the couple of example problems that I have given you to solve. I would like you to kindly see these problems, kindly understand these problems, and in case of any doubt, we can obviously, I am there in the next class, so we can obviously discuss those problems, and kindly tell me if you have any other problems via mail. Then maybe we can even discuss those problems in the class, and I can keep those uh, problem statements as the main class content. Okay, so these are the things that you have to do. So these are the set of problems that I would like to do yourself. These are these 4 problems. Kindly note it down. So this is another problem. I please also note it down. I would like you to find out the Fourier transform both the signal, that is of the unit step as well as for the modulus function. Okay, so this is important. This is the result is also very important. This actually will help you to understand this, and please do it. Okay, these are the 2 example problems from this slide. There is another problem. I would like you to solve even this, that is x of t is equals to e to the power of at into ut, and kindly find out the Fourier transform for this signal. Okay, now these are the things that I would like you to do. So do you I think actually I am done for this class. If you have any doubt, kindly tell me. And if it is not, then it's fine. Then we can wind up the class. Okay, then thank you. Okay, bye. Any doubt? No, isn't it? Okay. Okay. So, I have you noted the problems that I have given you to do? Okay, okay. And was it clear? Did you understand? You had some doubts, so where it's clear now, isn't it? Okay, okay. So, do your assignment problems. Any doubt, then you tell me. Obviously, as I said, I cannot solve this, but I can help you in case if you are facing any problem. Okay, sure, sure. Okay, then we'll meet in the next class. Thank you.